Tonight, we're going to have a follow-on presentation to last month's speech about astrophotography. Tonight, our presenter will be Ballard Bear, one of our club members, who is going to talk about the more classical way of doing astrophotography rather than Greg Dulcas's method of doing it more quickly. So, Ballard, I know that's a lousy intro, but
no, that's fine.
You'll clean up after me.
Yeah, we'll discuss it and people get the idea. Okay, we're going to talk about mainly is using a monochromatic camera for astrophotography rather than an actual color camera. And it has some advantages. It also has a few disadvantages, and we'll talk about some of those. And we'll talk about how you take these images and then a little bit how you process it. And we'll be following up with a bunch of examples at the end to show what some of the differences are that you can do with a monochromatic camera. In fact, most of the the big observatories, they're all monochromatic. They don't use these little color cameras. They use monochromatic cameras. There's actually a couple different types. There's the standard CMOS, which is what's used predominantly by amateurs. There are the old style CCD. They don't have as high a resolution with the CCD, but they have a few advantages, but a lot of disadvantages. They're real slow to download. Anyway, without further ado, we'll start talking about this. I'm going to start with a few definitions here of some terms I'll be using regarding the taking of the pictures. Some of these are specific to using a monochromatic camera, some are not. I'll be talking about narrowband filters. Some of you may have heard of these. And for astronomy, what you're doing is you're taking a look at a very narrow band of frequencies or wavelengths of light. And we can pick filters that a lot of nebula really glow brightly in. And so you can narrow it down with these specific filters. That you can buy them. They're 3 nanometers wide, some of them up to 12 nanometers wide, which is the wavelengths of light that they let through, the range of the wavelengths they let through. And the narrower the ones you get, the more expensive they are. So another thing we'll be talking a little bit about is what are called parafocal filters. And parafocal just means that all the filters, when you stick a filter in there, it'll change the focus a little bit. But if you get a nice set of filters, all the filters change it by exactly the same amount, so you don't have to refocus between each one, which is nice. Again, they're not cheap filters, but they'll do that for you. And because of the way we do things with monochromatic cameras, you might have to take pictures of the same object over multiple nights. And so we'll see that plate solving is a real nice thing. Plate solving is basically a huge database of stars that you can have in your computer. And with some software, and you can actually hook it into some programs, and it'll take a picture of the sky for you, and it'll tell you exactly where you're aimed. It'll compare it to the image. And if it's not exactly where you want to be aimed, it can actually adjust it for you, which is real nice. So there's some software to do all that. So you can take your pictures one night, and then to make sure you're exactly the same spot, you get it real close, and then you say, let's do a plate solve on that and check it, and it'll automatically move the telescope around till it aims right at it for you, which is really handy. One of the techniques, now this next one, dithering, is not necessarily something you have to worry about from, it's not really a color or monochrome thing, but it's something you can do to kind of even out the pixels between images. What you're doing is you minutely between images, you'll take a picture and then you'll move it over a few pixels and take another one, move it randomly in another direction, take another one. And you're only moving a few pixels at a time. And the idea is you're trying to get little parts of the image to hit different pixels so that you don't, if you have a hot pixel, you're not going to go ahead and emphasize that one. You're going to average it out if there's any slight differences between each pixel. And so that's what dithering is, and we'll do that. Yeah.
Does that mess with your focus or make your image blurry?
Well, you don't do it while you're taking the picture. You do it in between each picture. So you take a picture and then you dither it, take another one, dither it a little bit, take another one, dither it.
But when you stack them, they all line up over each other.
Right, exactly. That's what's called registration. And when you register the images, we'll talk a little bit more about that. You get them perfectly aligned. So you know, even if they're rotated a little bit, you don't normally want to rotate them, but if they are, it'll still line them back up. So that's yeah. So when you register it, that fixes that. And sometimes if you did there a lot, you'll see you might lose the very edge of the picture because some of the picture might be in one frame and not on another. So you'll kind of have a little line around the edge, but it helps clean up the image. Usually you don't care if you lose just a few pixels around the edge. So that's what dithering is. We use the term subframes. Sometimes we'll call them light frames, but or lights is another term for them, as opposed to some of the calibration frames, which we'll talk about in a little bit. But subframes are the individual frames that you're going to take and that you stack to build the image up with. So we'll use that term subframes a lot, or light frames. One of the things, this gets back to that registering thing. One of the things you want to do is you want to pick one of the individual subframes and you say, this was a really good one. So I'm going to go ahead and use that as the reference frame when we go to register everything. So everything will be registered relative to that frame. So everything will line up perfectly with that frame. And you do it for all the pictures you take, no matter which filter you used for the object. So those were a few terms I wanted to make sure we got started with. Like I say, I may use some other ones if you're not familiar with this stuff. So go ahead and raise your hand when you have a question. Okay, you might wonder, why do you want to use a monochrome camera where a color camera does it all for you, does all the colors at once for you? Well, you can use filters outside of the standard red, green, and blue, and these include those narrowband filters. And those are really, really handy, as you'll see in some of the examples at the end. You can bring out details that you can't even begin to capture with red, green, and blue by doing this. So that's really handy. Another thing you can do is you can pick which color you want to be the luminance. In black and white, typically what it does, or with color cameras, it takes kind of an average of the red, blue, and green and averages the intensities to create what's called the luminance image. And with monochrome camera, you can pick, what am I going to use for the luminance exactly? Now, you could probably do that by separating the colors out and making your own hypothetically with color, but it's real easy to do with a monochrome camera. And I've taken advantage of that in a couple of cases. Even with some planetary photography, I found that using something other than the actual luminance filter can sometimes be really useful for the luminance frame. Since it's all black and white, you can pick what color goes with what, which is real neat. When you're using a regular color camera, you all familiar with the RGB type sensors, where they have a red, green, green, blue pattern over the little tiny pixel or little tiny filters over every individual pixel. That's what a color camera does. All cameras at their lowest level are really monochromatic, but by putting these little filter elements on the top over the top of the pixel, you have you've made the camera quote unquote a color camera. But what it does is it records the color channels based on which pixel has what filter on it. But the other thing it does is, since some of the pixels have like a red filter over it, what they have to do to get a green point at that particular location, since that's the one with the red filter, they will interpolate between between the blue filters, or the pixels with blue filters, at about that spot. What should the intensity probably be? So that's how it kind of makes a blue pixel where there really isn't one, but it kind of figures out what it should be. With the monochrome camera, every pixel is being used as it really is with the filter over it. So you're getting the actual color at that instant. The RGB works pretty well, though. I mean, in general, it averages things nicely and does a good job, but you're not as accurate in a sense with a color camera that way. One of the things you can do too is when you're taking with a color camera, you're taking the same length exposure for all the colors that you're using. With the monochrome camera, you can determine what's the frame length or the time length I'm going to expose for, and how long and what gain am I going to use, things like that. You can actually change what you're doing on a per filter basis. And this can be real useful when you're doing things like the narrowband stuff. because you have to take very long pictures to pull the narrowband because it's such a narrow spectrum. You can take much longer pictures, and I'll talk a little bit more about that here as we get into it and show you a sequence that I've used in some of the shots. The other thing you can do is, let's see. Oh yeah, some of the downsides of using a monochrome camera. Well, you got to have a filter wheel, and you got to get filters, and they're not cheap, especially the good ones. You can easily spend $1,000 or more on a set of filters if you want LRGB and some of the narrowband filters. So they're not cheap filters by any means. It takes more processing time, probably a little more processing power. In fact, I had to bump my main machine up to that 16-core machine for doing some of this stuff. And there's a bit more learning curve on how to process these things. So that's one of the downsides. And of course, you require more space because you're taking all these images, and I keep them all just to keep track of it all. So you've got a lot more space that you're using on your computer. In fact, I went and got myself a little NAS server. So I've got a 60 terabyte NAS server in the other room that I use for storing all my data on with a RAID 6. If you're familiar with computer technology, RAID is a redundant array of disks, of independent disks. Well, RAID 6 means I can lose any 2 drives and I can still reconstruct the entire data set in it. So you have 2 drives that that are kind of dedicated to what's called parity. And if you lose one, you can reconstruct it. You lose 2, you can even reconstruct the data. And hopefully you don't lose more than that at any given instant. So that's one of the things you can do, or that's how I store the data anyway. Okay, specifically about the narrowband filters, there's 3 primary narrowband filters you use in astronomy. In fact, most of the Hubble images use these same sort of things, especially the ones where you see these real blazing colors on them. They're really done in what they call false color, or the Hubble palette. And you're using hydrogen alpha, which is called HA, oxygen 3, which is doubly ionized oxygen, sulfur 2, which is singly ionized sulfur. The reason they call it sulfur 2, sulfur 1 means there's no ionization at all. It's got all its electrons. Sulfur 2 means one of its electrons has been stripped off. Oxygen 3, for instance, 2 of its electrons have been stripped off. And when those things glow, they glow at very specific frequencies of light that these filters can really pull out. And we'll see some examples of that in some of the imaging. And like I say, these are very common colors, especially the HA and O3 in a lot of nebula. Even some of the planetary nebula, like the Dumbbell, has a lot of HA and O3, particularly O3 in Dumbbell Nebula. And even like the Ring Nebula, there's this faint halo of really interesting looking hydrogen alpha all the way around it that you normally don't see, but you can catch when you use one of these narrowband filters. And the frequencies of these things, like on the slide set, you've got 60.28 nanometers is the main frequency of the hydrogen alpha. That's a real red color. Oxygen 3, there's actually a couple of bands there. One's at 507.7 nanometers, the other's at 495.9. That's kind of a blue, almost a little bit towards the green, so it's kind of an aqua color to our eyes. And then there's sulfur, which has a couple of other bands that are around 6170 nanometers and 67.3 nanometers. And both of those are very red. In fact, they're redder than the hydrogen color. In fact, if you take a picture with a color camera of a lot of nebula, you'll see red. And that's because all you're getting is you can't differentiate there between the hydrogen alpha and the sulfur. They're going to both be red, so you can't really tell they're there. But with a monochrome camera, since you can separate these out with these filters, you can then assign them to different colors. In fact, that's what the Hubble palette does. So you can really see where these elements are. And it really makes some of the really outstanding images that way. And I'd mentioned this, that it sometimes takes a long time to, I'll take 8 to 10 minute exposures per frame a lot of times for in fact, I've even done 15 minutes at a time sometimes per image for some of the dimmer narrowband imaging. And you can assign the colors, like I said, the Hubble palette, that's where you assign the, even though it's a red color, the hydrogen alpha, you assign that to green, and you assign the sulfur to red, and you assign the oxygen to blue, which is pretty close to what it is, except for the hydrogen alpha, which is really a red color, but assigning it to green, and then you get this real pretty image where you can really see where the different elements are located in the nebula.
Excuse me, I have a question.
Yeah.
So your last comment there around light pollution and moonlight, and this is probably a long answer, but maybe, you know, there's a dummy's response to this, which I'm the dummy. Light pollution and moonlight. I know I've seen filters to eliminate that. What is the rough frequency ranges for those?
Well,
I mean, how?
yeah, they're mainly in the visible range. Now, the light pollution can be anything from sodium vapor lights, which has some real strong lines in the blue and green, but they're very specific lines. In fact, sodium vapor lights are very red, and the low pressure are even redder, and they're real easy because there's only to filter out because there's a couple bands there. Moonlight is pretty much reflected sunlight, so it's a lot of everything. But because you're looking at this narrow band, you're not polluting with all the other side bands coming in on your image that will get through in the RGB filters. So you can actually take some filters even when the moon's out. In fact, I'll show you a couple that I took that way, and with the moon being fairly bright, you know, and it's first quarter stage. Now, you don't want to be right next to a full moon, of course. You're going to get some effect from that. But if it's on the other side of the sky and it's, you know, first quarter or waxing or waning gibbous, and you're looking at the other side of the sky, it's not going to bother you much, while it will bother you a lot with an RGB image.
Thank you.
So yeah, so the narrowband really helps for that sort of thing. And of course, you can combine narrowband images with color images and get some really nice effects, which I'll also be going over in a bit. So you want to take your color picture, your normal color pictures when the moon's not very bright, and then you can still keep going even at when the moon is later in the week. Okay, one of the things I also do whenever I'm taking pictures is I also want to take a look at the intensity of each individual filter. So I'll take a few test shots and look at the histogram. One of the things I want to avoid doing is having too many pixels that are getting saturated. Here you can see there's a bunch of them right at the 65/535. That means that pixel is saturated. Those pixels are being saturated by the image. It's all right to saturate a few, but you don't want too many there, because if your red, green, and blue all come out saturated, guess what you get? White at that point. There's no differentiation. So I can tune the gain down or tune the time down, that, you know, the time I take each individual frame down accordingly. That way I can preserve the color a little better in some of the stars. A lot of times I'm not too worried about it because it's only the very center of the star image. It'll be very bright. And because real bright stars tend to bloat a little bit because their light gets scattered around in the sensor itself, making the stars a little bit bigger. You'll still probably get a lot of the star's actual color from that, but you don't want too much of it. So that's why I always do a few test shots and look at the histogram before I actually go down and say, this is what I want to do for this set of pictures. So that's one of the things. And if you use like an ASI camera, they give you some software for deep sky imaging and stuff. And I use that just to do a quick test and get the histogram and take a look at it. Okay, here's an example of one of the sequences I was doing for, this is a picture I was taking of M65 and 66 on a 4,000 millimeter focal length. So it's pretty big. And in this case, you can see I was taking some luminance, and you notice on the luminance pictures, I was taking those at 120 seconds, and I was repeating it 60 times. But on the RGB portions, I was taking those for 4 minutes each and taking only 20 of them. So I emphasize the luminance more because that's where all the detail is. But I still wanted to get a decent amount of color in there, so I took a number of those. And then if you look at the hydrogen alpha I was taking also, you can see I was taking those for 500 seconds each and taking 20 of those. And by doing that, you can that's one of the things you can do with the camera when you're using individual filters. You can kind of pick and choose what you do on it. And you can adjust based on, like I say, what I saw on the histogram on the previous image as to how deep I want to go or how long I want to go on a picture, and then get a feel for maybe how many pictures I want. Some of that's judgment and some of it depends on how much of the noise. The more images you take, in general, the less noise will be in the final image, the less graininess. Hard to get it all out, but you can get a lot of it. And just like in color cameras, Greg went over this a bit, you can take these calibration frames. You've got the dark frames, which are basically made to subtract out thermal noise in the sensor. So you take darks at the same temperature and for the same length of time as the lights. So in my case, I had some lights that were 2 minutes and some that were 4 minutes in that previous example, and some that were 500 seconds. I needed darks for all those different times. Now, and then you can have flats, which in effect are really, the way I take them is I put kind of like a pillowcase over the front of the telescope. And so I've got this whitish color coming in, and then you're looking for any vignetting in the image as it comes through the optics. And also if there's any dust, it'll be able to subtract that out later. So you're calibrating how the optics generate, how bright an image they generate across the image. And by putting a t-shirt over the top and aiming at the blue sky, you're kind of getting an idea that it should be evenly illuminated. So that's what the software is going to try to do. And since your flat frame is not going to be completely, it's not going to be absolutely perfect, you'll kind of see that it's usually a little darker towards the edge, and the flat frame will help the code change the pixel intensities at those points in order to make the frame flat. So those are what flats are. Dark flats are another type. I think Greg went over those. And basically they are dark frames taken for the duration and time and temperature as the flats. In a lot of cameras, you don't necessarily need to do that because if they're really short, you don't have much thermal noise to get rid of. There can be sometimes I've seen where some of the older sensors, they had what they call sensor glow or thermal or some glow, because in the CMOS sensors, the actual electronics for doing the A to D and everything is right on the chip itself, right on the sensor chip. And those used to have some thermal glow from just the sensor heating up. They've gotten really good though in these newer cameras at completely cutting that out. I've never actually seen it on my newest camera, so I don't have that issue. Now you could have a few frames that are get bright that don't show up in the dark frames when you shine a little bit of light on it, and dark flats can help with that if you notice any of that. And basically, if you do, you'll find that you'll when you put a dark flat out there, you can then subtract out any noise, which will end up looking like a dark spot on your frame when you do it. Because in effect, if you take a regular flat, it's going to have a bright spot, which will get averaged out and make it darker than it should be if you got a hot pixel that comes up when a little bit of light gets shined on it. I've not seen that. Most of the cameras, I think, Greg, you've seen some of that. I haven't actually had that happen. So normally I get by with just the darks flats and bias frames. Bias frames are really to measure the electronic noise. And what you do is you take a bunch of, basically they're dark frames as fast as you can, you know, whatever the maximum rate your chip can take them at is. And what you're trying to do is measure the electrical noise of the read of the sensor. And so that's kind of a thing to subtract out there. Now, just like with color sensors, you want to do guiding, and like I mentioned before, that's where plate solving can really help if you're doing it across multiple nights. And I do that almost all the time. I go over multiple nights. Hardly ever do I get a one night set of images. The rotational image orientation, you want to keep it the same. If you don't, you'll still get the center of the image and the registration will bring it around. But since the sensor's kind of a rectangle, if you shift it a little bit, each image would get a little bit different pictures. So you're going to end up having unevenness around the edge that you have to crop out. Now, it's not a problem when you do the meridian flip. Everybody know what a meridian flip is? That's where the telescope, when you're going up over the zenith, all of a sudden with a German equatorial mount, the scope just can't keep going that way. It'll start to hit the mount. So it has to flip around and then start working back on the other side. And so you've done a 180-degree flip of the scope from one side of the mount to the other to continue taking your images. That's a meridian flip. So in effect, the pictures now are 180 degrees different than they were before. Now that's not a problem because the sensors are square, or rectangular, or some of them are square, but a lot of them are rectangular. So doing a 180, you're still getting the entire image if you center it exactly the same point. Plate solving helps that too, so that once you've done the meridian flip, you're aimed right back where you should be once the mount has flipped the thing over to the other side. If you have a fork mount, you don't have that problem. Fork mounts can just keep going. But German equatorial and some other mounts, once you get above the zenith by 10 degrees or something, you'll start, in some locations, you kind of hit the pillar as you're coming around the backside. So that's what one thing plate solving also helps with. And like I say, you flip the image 180 degrees, so you don't lose anything. You get the same image, and registration will reorient it correctly for you, and you still get the entire image. And as far as guiding, you can do guiding with either a separate guide scope or an off-axis guider. And I've done both. And there's some cases I need to do one versus the other, and I'll talk about that in a little bit. Here in this next slide, I'm showing an example where I told it to do the plate solve. The first time it did it, said, oh, we're off a few thousand pixels. And I think I set a limit of 10. So the code said, okay, we'll try again. And it moved the scope for me. And it said, okay, now we're within 6 on one and 5 in the other angle. That's great. And it did the plate solve. So then it could go ahead and start taking its pictures. So with the automation software, you can really do some neat things like that automatically. Everyone following what I was talking about with the plate solve there? Okay. Now, the other thing you do is when you're guiding is, I only threw this one in to kind of show you where I'm dithering. Now, this is where it's tracking, and you can see this was a really good night. The image was staying within about a quarter arc second of where it was supposed to be. And you can see a little bump right there at each point where it's dithering. If you look closely, it points out that, oh, we just did a dither there and a dither there. Now, so those little bumps don't actually show up in the pictures because the picture had stopped at that point. It dithered it, recentered, or waited for the image to settle back in or get its guide star back in place, and then it started the image again. So you can see the sequence of events where between each frame, I was telling the software to go ahead and dither the image. Now here's an example on the left. I've got a setup there where I had to use a separate guide scope. And the reason I was using that big camera lens on there on the left side. And you can see there's a filter wheel hanging on it and the camera behind it. But in the case of the camera lens, I don't have enough back focus to actually add an off-axis guider on top of the other equipment there. So in that case, I was guiding with a refractor that's kind of pinned next to it. Now in the bigger scope here, I've got plenty of back focus. So in that case, I've got an off-axis guider. And I really like to do that, especially at these long focal lengths of around 4,000 millimeters, because any slight flexure will really screw up your image. And with the 500 millimeter, it's a lot more forgiving. That's 1/8 is, you got to have 8 times more flexure before you'd ever notice anything than with the big scope. So if you get real long focal lengths, off-axis guiding is the way to go if you can. Does everyone know what I mean by off-axis guiding, by the way? That one little device that's kind of just in front of the filter wheel, it's got a little prism going down that captures a little bit of the light, and it beams it out to another little camera, small little CCD sensor in this case, that picks up the image and watches the star, and then the scope is watching using that or the software is looking at that little image of a star on that camera and keeping the thing just perfectly aligned for me, making minor tweaks to the mount to try to compensate for any variations that are occurring as the refraction of the atmosphere changes, as you're changing elevation, or little waves of air come by. So it does a pretty good job that way. Okay, once you've taken all these images, like I did, you saw that sequence in there, I had red, green, blue luminance, and hydrogen alpha. Once you've taken them all, you got to store them in some sort of directory structure that makes sense. So here's the one I use. You could do whatever you really want, but what I tend to do is I'll have like Nebula XX or some name of the object, and then I'll have a blue, green, red, luminance, HA, whatever. And below that, I'll have the light frames that I've taken, and then I'll have directories for the good frames once I picked which ones I think are good, and then which ones are, then I'll take those good ones and calibrate them, put those in the calibrated directory, and once I've calibrated them, then I'll register them all. And I'll typically, one of the good ones is one of the ones usually out of the luminance is where I usually pick the frame that I'm going to use for the reference frame, which I'll talk about in a little bit. And then once I've integrated the set of frames, I integrate each set separately. So I'll integrate blue, green, red, and I'll store the integrated image there for blue, integrated image in green, etc. And then there may be, some denoise or some star shrinkage or something like that you do. Some other techniques to improve the image that are specific to a specific filter. So I'll store that with that directory. And then outside of those directories, under the nebula itself, I'll have the finished products that I put together. And again, you don't have to do that, but that's just the way I like to store things, just to keep them organized as I'm going through it. Now, this chart here shows how do you figure out which frames are good and which ones are not. Well, I run it through what's called a subframe selector. And in this case, what I'm comparing is what's called the FWHM, which is the half width half width full maximum size of a star. So this thing, when it goes through it, it analyzes all the stars on there, sees how big they are, and it says how big is the image of the star at its when it gets down to about half the maximum brightness. So it goes through and calculates that. That's a real useful indication of how blurry the image got because of the atmosphere and things like that. The other thing I like to look at, and in this case, I pick stars, the number of stars it sees. And usually when the FWFM is real small, you get a lot of stars because it's really tightly focused at that point. Not always, but usually. Sometimes a cloud will go by and you still might have a really good, focus, but all of a sudden the star number drops. So I'll typically throw some of those out too. And so I go through and pick which ones are, like the ones that really have kind of a large FWHM or kind of big. I throw those out so I don't pollute the rest of the pictures with them. And usually you can see there's they have guidelines on there, and I kind of pick and choose based on what I found works for my pictures. There's other things you can do. You can look at the eccentricity of the stars and the power function of the stars, different things that this allows you to do. But these are the two that I normally use for determining which pictures are good and which are not. And all the ones that I didn't X out, these are going to get copied into the good directory that I'd mentioned before. And they'll have a little underscore G or A for accepted on them to indicate that they've been accepted. Then comes the time where once you've got the good ones, you have to calibrate them. And here's where I put in the dark frame or the bias frames and the dark frame and the flat frame and tell it to calibrate all of them. And then it dumps those into the calibrated directory for me. These were a bunch of HA images on the Soap Bubble Nebula, in fact. And once you do that, then you tell it to go ahead and register them. And it turns out I was using, in this case, for luminance, I was actually using the HA in this one. But the HA reference frame, this is one of the real good ones. If you go back at the other slide, you'll see that this was one of the really good frames in there. And so that's the one I picked for the reference frame to line all the stars up. Then I'll do that on all the green frames I took and the oxygen 3 frames I took and the sulfur 2 frames I took of this thing. And then after you do that, you go ahead and integrate them all. So you take all the registered frames and you stack them together. And in this case, I used average additive with scaling, which is a typical thing you do for stacking frames. And I picked some values for what I was going to do for the noise removal and things like that. And when you get done, what you get is you get 3 images. You get one is the stacked frame, one is the low rejection, one's the high rejection. Now, all these frames have been stretched a little bit already. They all look pretty black except for the main frame, where a few bright stars you'll see before you stretch it. So I stretched them, and this was just a temporary stretch on the stacked image. But you'll see that kind of haze that's in the high rejection. If a satellite had come back, I'm surprised one didn't in this case, because I usually get satellites coming through. You'd see a light streak coming through it, because what this does is it compares all the frames and it says, is there a limit, kind of limits how much different can the pixels be between frames? And it'll figure out that, oh, okay, these had a few hotter spots, and that's besides the normal dark frame subtraction. So it'll go ahead and subtract that out for you. And usually I hardly ever see anything at all in the low rejection, unless you screwed up your calibration somehow. That's the only time I've ever seen low frames have something in them. So this is using Pixinsight. Like I say, this program has a lot of capability, but it's got a really steep learning curve. But you can do all sorts of fancy manipulation with it, which I like to play with. And you can tune parameters. Like if you still see a satellite, for instance, in one of your images, you can tweak up what sensitivity it does on the high rejection, and you can actually eliminate it. Now, if you got a 747 coming through, you're probably going to just throw that frame out. But if it's a satellite, you can usually subtract it completely. The next thing I do is I'll take and do a little bit of noise reduction on the frames. And there's this real neat program in there, or process, called multi-scale linear transform. And basically, it's looking at all the different wavelet layers in the image. And you can actually, there's a script to actually analyze the wavelets beforehand, but once you've seen it a few times, you know what to do. You'll see, like, if you look closely, I don't know if you can see it on your screen, but if you look closely, you can see that there's some graininess in the image on the left. And on the right, there's hardly any, because that's the one that was processed. But we really didn't change the stars much. You look at some of the stars. Now, both of those images, they're the same, but they're shifted over. But you can find some of these same stars over here. And you see the stars are really about the same. And the nebula is the same, but you've softened all the graininess out. And so and I do that for each frame before I go ahead and combine them. So I do that. Actually, this was done before stretching, but I do what's called a temporary stretch just to see what it looks like, so I can actually see that happen. And then the next step is to stretch it. And when I stretched this one, I looked and I saw that, well, you can see the soap bubble in there. It's kind of hard to see. You can kind of see it in there. It's real faint. But what I realized, I'm going to want to brighten this image up. And if I brighten the image on the left up, that's going to brighten those stars even more. So one of the things you can do is you can create a star reduction mask. This is something I don't always do, but on this particular image, it was necessary. And so you can see that mask, it's got like a whole bunch of little donuts in the mask. Each one of those is a star, where it's letting the central part of the star come through. But what it's going to do is it's going to change the luminance part of the image for each one of those stars and bring them down a little bit. So if you look at like the stars on the left and right, those are the you'll notice they're a little bit dimmer on the left. And the reason I wanted to do that is, like I say, I'm going to brighten the image up in order to bring out that bubble nebula, or that soap bubble nebula, later on. So that's a real handy thing. So I ended up doing that on all of the images. And then I go ahead and do the LRGB combination. Now, in this case, LRGB It's not really luminous red, green, and blue in this case because you can't really see much of this nebula in red, green, and blue. In fact, if you looked at the green image that I took, you wouldn't see anything at all of the nebula. In fact, you don't even see that nebula in the sulfur. You only see it in the hydrogen and the oxygen. But I wanted to get something that kind of approximated what the rest of the nebula and everything looked like in a true color fashion. So I assigned the hydrogen alpha to red, and I used a green channel, or actual green picture, as the green, and I used the oxygen 3 as the blue. And that's what came up with. I had to do some, the green was overall too bright, so I had to do a little background removal of that. But it still needed some color calibration at this point, and the brightening that I was talking about. And so those are just some things you can do really easily with some of the curves transformations within the program. And here's what you get. So here's the image of the soap bubble nebula, that previous image, after I brightened it up and did a little color calibration on it. And so this is, like I say, using hydrogen alpha for red. Green is actually the green filter, and the blue is the oxygen 3. So you may have seen pictures like this. This is a real hard one. This is about 30 hours of exposure to get this sucker. So he was a real dim one. And then, of course, you can do the Hubble palette. And here, what I did is I used hydrogen alpha for green. I used oxygen 3 for blue. But in this case, I had another 10 hours of sulfur 2, that I added in as red. There wasn't a lot of sulfur there, but you can see there's kind of some yellow on the side there. And that's the combination of the green and the red coming out. So these are the sorts of things you can do with a monochrome filter that you couldn't do with a regular camera. Now, here's another neat thing I wanted to point out. You don't have, how do you pick and choose to assign things? You can do kind of however you feel like it. So on the left is an LRGB image of M33 I took with a refractor. The image on the right is the same thing, except I didn't use red for the red channel on that one. I used hydrogen alpha for the red channel. And it really jumps out where all the nebula are in the star forming region. So it kind of comes out neat that way. So it can give you new information, and it makes for a real pretty picture. Another thing you can do now, this is with that with a 500 millimeter camera lens. This is a LRGB image of the or not LRGB, narrowband image using the Hubble palette of the Cone Nebula in Christmas tree cluster. And it's a real pretty thing to look at, but when you zoom in, you can really see some neat detail. Like you see that at the bottom of the image there on the right-hand side, that's the zoom in of that section. Notice that one, it looks like it's called the Foxfur Nebula for good reason. If you take a look at the bottom left there, you'll see that you can almost see the fox's face in it. You see all that furry looking nebula. You don't see that at all with LRGB. It just doesn't come out. And again, this is the Christmas tree color cluster. And the Cone Nebula is up in the upper left there. So you may have been familiar with that if you've looked at it, but it's a nice one. But with narrowband, it really pops it out for you. I've got some in my website, some LRGB versions of this. You can take a look and see what the difference is. We can take a look at some of those after, because we're almost through most of this part now, and I can bring up the website and show some of the other images of these things. But it works really well. In this particular case, a lot of times when you first add narrowband images in the Hubble palette, you'll get kind of magenta stars. And so I usually will do a magenta subtraction, and that's what I did in this one. So I got rid of the magenta stars in some of these. In fact, a lot of the Hubble images, some of them, they don't do that. And you'll see all these magenta stars all over, and that's why, because that's what kind of happens when you do narrowband imaging with the Hubble palette. But just adding a little bit of magenta or subtracting a little magenta out of the image really pulls the stars into closer to real color. Now, here's another example. Like I had mentioned before, a lot of nebula come out really red. Here's the M16, also known as the Pillars of Creation there. And that's on the left is an LRGB image. There's the image on the right, same image, except it's using narrowband completely. And if you look at that one, you can see all sorts of detail and information in it. In fact, if I go on the webpage, we can zoom way in there and see all little, see a bunch of little detail on this guy, which came out. So this is one of the reasons I really like the mono camera, because you can use this narrowband filters to pull this sort of information out. You can see that there's some yellow down at the bottom there, which is the sulfur, and you can see a bunch of the oxygen in the middle, which is the red, and then the green is all around. Sometimes you have to tone the green down a little bit because it's so overwhelming, because hydrogen is one of the most common things out there. In fact, I've got some examples of the Rosetta Nebula that way, where I just did it straight and the whole thing almost turns green because of that. But if you tone it down, you get some more information. Here's one I did just the other night. This is the Dumbbell Nebula. I wanted to do some narrowband imaging on it. So here's on the left is the LRGB image, which came out pretty good. On the right is the same image, except what I did is I used a process where you can, rather than completely replace the filter, you can just add specific narrowband images onto the image that you already have. So here I added to the red channel some hydrogen alpha, and I added to the blue channels some oxygen 3. And now all of a sudden you can see these kind of clouds of extra stuff that are coming off it that you didn't really see in the LRGB image, which is kind of neat. Now this one I also did some HDR processing on it to really show some of the texture inside the nebula. And to give another idea, here's just the luminance filter taken of Orion. Here's a hydrogen alpha filter taken of Orion. And you can see they're about the same intensities, but you can see there's some nebula or something around it in the luminance. But in the hydrogen alpha, all of a sudden you see all the detail in the nebula that you don't see otherwise. So that's one of the real nice things about using the narrowband imaging. You really pull out detail that you don't otherwise get. Notice that in hydrogen alpha, you don't see the running man hardly at all, though, but you do see it in the luminance image. So it's just a matter of where the nebula happens to be bright at. Okay, that pretty much goes through what I was going to talk about. I can bring up some of my other images and show you a few other examples, which are kind of neat if you want. And everyone's welcome to go to this website and look around. And you can download anything you want. Some of them will take a bit to download because they're pretty big images.
Yes.
Okay, there's the Ring Nebula and LRGB. Now here's what happens when you add the hydrogen alpha. And if we zoom in, might take a moment to fully download. You see all this other detail. Now in this particular case, I had to kind of mask off the center of the hydrogen alpha because everything turned red at that point. But I wanted to get that faint filament around it to show where that was. And that's something neat you can do with some of these narrowband images. So you can combine things as you choose. There's a dumbbell. That one was taken with the DSLR. And there's the one we were just looking at. And you can zoom in on these images in here. Sometimes it'll take a few moments to download the full image when you zoom in. I guess that's pretty close, but yeah, sometimes some of the images take a while to download. So yeah, there's the Hubble palette version of the dumbbell, which is kind of neat. Again, you can see where the specific gases are, the colors of the images. Here was the Crab Nebula. This one was, you remember the one where I was showing you the dithering and the tracking. This is the object I was taking an image of that night. Got to wait for a few moments for it to, okay, there we go. Yeah, you can see right there, there's in the middle. Can you see the little hand on it? That's the neutron star right there. And those are some shock waves coming off it right there. So you can get some nice detail on that puppy.
Okay.
So,
Questions?
yeah, any questions about anything?
I don't have a question. It's just amazing. This is incredible.
Yeah, I like to play with the image like in this last one of the Crab Nebula. I stretched it out more to see some of the kind of the IFN or the real faint nebulosity around it. So I wanted to catch some of that in there.
Ballard,
Yep.
the neutron star you pointed out in the crab, is that the pulsar?
Yes. Yeah, here's an image where I've got it zoomed way in.
Okay.
Yeah, there's the neutron star, and those are the shock fronts coming off it.
That's incredible. And that's taken from the ground.
That was taken from my backyard. Yep.
Yeah. That's incredible.
What's the elevation of your backyard?
About 2,500 feet.
Yeah, you can still breathe.
Yeah, you can still breathe. Yeah. Yeah, let's see. I don't know if you can see. Oh, no, it's too bright out there, right?
There's an awful lot of gas in the off to the left towards the brighter star there.
Yeah, I'm not sure what that is, but it's actually real.
Yeah,
It's in all the images.
I gathered that, but yeah, wow, look at that.
Yeah. You can see that there's this kind of reddish glow there.
Yep.
So there's something out there.
And
That's real. It's really there.
Would that be hydrogen in that case or sulfur?
Probably hydrogen. I don't think I actually did an LRG. I didn't do a Hubble palette on this one, so I can't tell for sure. If I'd done a Hubble palette, then we'd be able to tell.
Okay.
But I hadn't done that at that point on this one. This was just LRGB and some different types of processing to pull it out a little bit.
No, I'm just amazed at the amount of information that is there in a quote amateur image.
Yeah, now you can do some good stuff with a little practice.
Yeah, apparently.
But yeah, so you can see a lot of detail in these guys.
That's very cool.
Yeah, there's the I did take hydrogen alpha this one. In fact, that was some of the stuff I'd added in on some of them.
Wow.
In fact, and that's just the pure hydrogen alpha. It kind of looks like that critter from Star Trek, the crystalline creature that in Next Gen.
Yes.
But that's what it looks like in hydrogen alpha. I mean, one thing I can also show you real quick is that I use a monochrome camera also for some of the planetary imaging. One of the things I tried was instead of using a luminance filter on some of Saturn, I tried a UV filter and was surprised at how much more detail I got.
Really?
Yeah, let me show you one of those. Here's one where I used UV for luminance on Saturn. And it came out really neat. You can actually see some of Enix's division there, and you can see Cassini's real well. Right. Saturn was actually pretty low in the sky at the time because, well, in the next few years, it'll be getting better because it'll be getting higher, so you'll be able to get better images.
Yep.
But this is probably a future talk we'll do maybe at the meetings next year.
I'm going to say thank you, Ballard, for the presentation. I certainly learned a great deal. And like I say, I'm not a photographer, but that's fascinating.